Okay, take
Very
it away,
good.
Pavel.
Yeah, hey everyone. Today I'm going to talk about statistical tests and how they work and details of how they work. I have a confession, I don't know much about statistical tests. I kind of know some sort of probability theory, and I always thought that probability theory and statistics are basically the same. But when I was preparing for that, I found out that it's not. So that was a discovery for me. So I guess in your work, if you're doing any kind of experiments and you have to compare results, you might have heard that you need to run a statistical test to find out if your results are significantly different or kind of the same. Uh, Papers usually require something like that. Uh, and so you probably use some tests. But um, personally, I do not understand how those tests work. There are a lot of variants of them, and it's not clear when you need to apply one or another. There are rank tests, there are single tail, two tail tests, there are same variants or different variants tests, and there are paired and unpaired, and it's a huge zoo that is very confusing to me. And so I decided to spend some time to figure out how it works and kind of develop a simple permutation test from scratch to figure out the details about it. So after I do that, I will get to the paper that Sergey mentioned. I don't know how much time we're gonna have, but let's see how it goes. So to start this foundational stuff on rederiving the permutation test, we need to understand what's going on behind the scenes in those tests. There is a mathematical thing called central limit theorem, and it works on distributions, basically. So imagine you have some kind of data set like x1, xn with n samples. They are sampled from some distribution. You can compute a sample mean like this. And also the distribution has some kind of real mean, grounded mean, and grounded variance. And so there are two laws that are telling something similar. One of them is called the law of large numbers. It's basically telling you that as your sample size grows, the sample mean is approaching the true mean of the data. And another thing is called central limit theorem. It tells you that as your sample mean is approaching this mean, the error between this sample and the real means is obeying the Gaussian law. As you increase the number of points, this difference gets smaller and smaller, and this thing in the denominator tells you about that. So there are many different ways to write down the central limit theorem. I guess we can take a look at this thing on the right.
Just
Yeah. Sorry. Okay. Yeah, thank you. I need to use one more. Yeah. So you can write the central limit theorem in different ways. This way on the right, it kind of combines both the law of large numbers and the central limit. So its sample mean is going to the mean, and the variance is explained by this. It goes down as the number of points in your sample is growing. So let's see some examples on how this works on different distributions. So imagine that we sample some data set X from this blue distribution here, and then we add the samples, and we see how the mean of this sum behaves. So this funnel on the left is basically showing this. Each blue line here is independent run, independently generated test, independently generated sample, sorry. And the n on the x-axis telling you how the sum behaves over the sample iterations. And so you see
But lines are misleading. There are no lines, right? You pick an n, sample n numbers, compute their mean, and put a dot there. How is 10 numbers connected to 15? There is no connection.
well, I mean, each line here, each blue line, imagine it like this. You start with one sampled number, then you add another one, then you add another one.
No,
And
but they're independently sampled. What do you mean add another one?
line is a different subset of the true population.
Yes.
Okay.
Each
Not
line was
just
some
each
divider.
line, not just. Oh, you adding those numbers to the set. You keep that first number in the set, and then you adding additional number to that set. Okay.
Yeah, each line is like an independent run, independently sample data set. Like maybe one line was sampled at Trend Center and another line was sampled somewhere else, and then we can compare them.
Oh, okay. So there are I don't know how many 20 samples, right? Each time you sample exactly 20 samples. But then to compute the mean,
Yeah.
you use one of them, two of them, three of them,
Yeah,
etc. Right?
yeah. And
Okay.
each line, yeah, I think you got it.
Okay.
And so, yeah, we see here that as we add these samples up and average them, we see that the sum is approaching the sum asymptote around zero. And as the n grows, this region gets narrower and narrower, and that's what central limit theorem is predicting. This is like 2 sigma variance, and it's going down, down, and down. Central limit theorem, the interesting thing about it is that it works with any, well, a lot of different distributions. They don't have to be Gaussian. The point is, in the end, they become Gaussian. So on this example, if you start with, if you have some dice is a uniform random thing, you can sample one dice throw, two dice throws, and so on, and other one. And as you do
Just a correction. Not the distribution become Gaussian, but distribution of their mean as estimated becomes Gaussian.
Yeah. Yeah, correct me if you hear something like that. And feel free to ask questions, please. So as you add the numbers up, the mean of the sampled mean approaches the true mean, and the variance, and the whole thing is looking like a Gaussian. And it gets narrower, narrower, and narrower. It works for uniform distributions. It works for bimodal distributions when you have two preferred things and nothing in between. Like here, with a coin flip example, it starts like this, then eventually it still goes to Gaussian. And it works with skewed distributions that don't look similar, but in the end they also become similar. Interestingly, there are distributions that do not obey this law. And if you remember in the definition, central limit theorem is operating with mean and the sigma. And in case when your mean, then your distribution doesn't have properly computed mean and sigma, it can break up. So an example of this is this Cauchy distribution. Its formula is shown here. Its mean cannot be computed. If you try to compute this integral, you get infinity minus infinity, and that's undefined. And the interesting thing is, if you try to add up different samples sampled from the Cauchy distribution, they do not obey the central limit Gaussian thing. They actually still remain Gaussian, Cauchy distributed. That's kind of dense, but let's also see this example. I tried to plot the same thing I did for the central limit theorem, but for samples sampled from the Cauchy distribution. And you see that they also have some kind of centrality. They have a preferred mode at zero, but as the number is growing, you don't see them actually getting closer to it. At each step, this sample mean remains under this Cauchy distribution it started with.
Spencer has a point to raise.
Yeah, just a quick clarification, just because I'm not familiar with Cauchy distribution. What is that? Can you explain a little bit, like what distinguishes this distribution, so that I can try to understand why?
Yes, Cauchy distribution is one of the Bell distributions like Gaussian, but it is wider. It is described by this equation.
Okay.
And so the problem with it.
So it's like a super Gaussian.
I think super Gaussian is narrower than Gaussian, right?
Yeah, I mean, this looks okay.
the Cauchy is wider than Gaussian. I think super Gaussian distributions are narrower. Oh, correct me if I'm wrong.
It looks like your tails are
They're too
flatter, but
Yeah.
your peak is narrower than
Yeah.
the typical Gaussian
Yeah, I
distribution.
wouldn't call it like a Gaussian. It's somewhat more super Gaussian.
Yeah, I'm not sure what super Gaussian is exactly.
Right, so super Gaussian distributions will tend to be narrower, peak higher, and have those longer flower tails.
Yeah.
So it's a very important thing to know for ICA, right? Because that's how a lot of infomix stuff work.
Yeah.
Do they have a smaller variance or larger variance, or it's not that defined then?
It's a differently defined variance, is how I would describe it, right? It's not defined, the tails are just different, right? They're shit, the curve, the density function is different. That's what how you should think about it, right?
Yeah. I think the thing about Cauchy, the tricky thing about Cauchy distribution is looks like a bell. It seems to have some kind of central line, most likely value. But you cannot actually compute the mean of this distribution, the integral is diverging. And because of that, you also cannot compute the variance and all the other higher momentums.
Yeah,
So, yeah.
from what I'm seeing, I'm also haven't worked with Cauchy distributions as much, but the distinction is that the mean and the variance are not generally defined, and there are cases where you can have them explode and the integrals aren't even defined, right?
Okay, got it.
Yeah, as
Yeah.
you have that, you have as much on your slide.
Yeah,
Yeah.
this is an attempt to compute the mean.
Yeah,
and
I got it.
the
I got it.
divergence.
Yes, I see now.
Yeah, and as you add them up, they do not get narrower, they still remain sufficiently. Okay. So central limit theorem is fairly, I don't know how to say. It's a thing that's spoken up in many real life examples. I guess if you ever trained a deep learning model, you know that we initialize weights in those models using some random distribution. And central limit theorem also manifests itself here. As the number of dimensions in your neural network is growing, the kind of variance of the randomly initialized model is also growing. And so people came up with an idea to compensate for that and limit the spread of the variance of the initialized model weights based on their number.
I think just you're conveying a kind of narrower, especially if you go like slides back, narrower interpretation of the central limit theorem, where you have definition of central limit theorems. This one, this is a narrow interpretation. Central limit theorem is wider than that. You are treating a sample mean xn as the thing needed for central limit theorem. What central limit theorem actually says is much stronger than that. Any sum of any random variables, they can be each one of them can be sampled from different distribution. Tends to sum of random variables tends to Gaussian. That's what it's proving. You don't have to have a sample from like here. It's a narrow. This is a special case because central limit theorem says sum of any co-distributed random variables tends to Gaussian almost surely as number of samples goes to infinity and blah blah blah. Then those variables in your slide, they all are equally distributed. They all come from the same distribution. Well, of course, so it's a subset of what we just said about central limit theorem. I think it's important. Any sum of random variables tends to become a Gaussian.
Kinda, yes, but at the same time, we showed this Cauchy distribution that sometimes it breaks.
No, when there is no
Not the means and the variance. I think that's the distinction. Correct me if I'm wrong. He's referring to the sum, which will be defined, right?
some of the random variables. No. But like if all the random variables are defined as Cauchy distribution, what Pavel says is they will not tend to Gaussian.
Yeah.
But okay, you continue. Let me Google that meanwhile.
I think, Sergey, the Cauchy distributions just violate the assumptions of the central limit theorem. I think that's all that it is,
Okay.
right? So
Yeah. I wanna check out the assumption because my kitchen definition of central limit theorem is sum of anyhow distributed random variables. I
Yeah.
didn't know there is a constraint on what distribution those variables should come from, but probably it is. Let me check while Pavel is continuing.
I think the assumption is the central limit theorem is going to work if your distribution has a computable mean and variance. If it doesn't, then it can explode. There is
I'll get back to you on that.
There is also a generalized central limit theorem. It kind of handles distributions like Cauchy that still have some kind of preferred mean and some kind of finite variance, but they still explode under the integrals that use the central limit theorem.
Yeah, I think it's the undefined variance and mean, Sergey, that are violated, right? That's just a requirement, of course, to have something converge. You can't have it, explode out to infinity, right? Or be like not exist, right?
Yeah. So when I was showing this slide, I agree with Sergey that it's kind of narrowing down, but it's more to exemplify how central limit theorem manifests itself in different situations. Yeah, it's talking about distributions, but you can use its findings to explain some other stuff and do engineering stuff like the random weights initialization to make them more stable. So how this central limit theorem is useful for statistical inference? We just talked about what it is and how it behaves, but what can we use it for? So we talked about that it works with sample means, and that it tells that the sample mean will eventually be distributed as will follow a Gaussian distribution. It gets narrower as you increase the number of points. We can use this Gaussian to estimate the probabilities of how likely different data sets are the same or not the same. If you have a Gaussian, you have some kind of probability. And if you can normalize this Gaussian to be a normal 0-1 Gaussian, and you can extract the probabilities there to use them as numbers that can evaluate how different your data sets are. It's like a way to introduce some kind of numbers into this comparison, make it more quantitative. Yeah. Okay, so any questions so far?
So go ahead.
So the correction, those random variables, the variance has to be finite. Cauchy distribution has infinite variance, so it cannot be used. But if the random variables are sampled from a distribution with finite variance, then there is this generalization, Lindbergh something CLT, that tells us the sum of those IID random variables will tend to Gaussian. Doesn't work for financial markets. Doesn't work for Cauchy distribution. Fat tails, infinite variance. So
yeah, I think I'm ready to move on to the next part where we are using the central limit theorem to rederive some kind of statistical test. Let's imagine that we have three kinds of dice, A, B, and C. Their distributions, the likelihood of each phase is shown on this figure on the top right. So dice A and dice B are kind of uniform, but dice A is biased towards the phase 3, and dice B is biased towards phase 4. And then there is also dice C, which is kind of biased towards 3, but it is less uniform than dice A. And the question is, can we compare those dice and figure out if they are the same, if they have coming from the same distribution or not? Is they the same kind of dice or not? And so we can do it. We can try to develop a test that will compare the dice die A against B and die A against C. So I sampled a random data set of 3,000 points for each dice. And so you see them there. They approximately following up the ground truth probability of each die. So what can we do with that? We kind of see that they are different. So we assume that we should be able to tell them apart. But how can we do it with numbers? We can do it using central limit theorem. So the transition between this and this, here for these results, I sampled many data sets, 2,000 data sets of each die, and I found their sample means. And these bells are describing those sample means. The gold lines here, they are the sample means of this example data set I showed in the beginning. So you see that they are different. Also, the distributions of those sample means are different under CLT. And also CLT is telling us that these distributions are Gaussian. So what can we do with that? We can compare the means of these sample mean distributions. And we assume that if the dice are the same, they should have the same mean. So we can check if they have the same mean by subtracting the mean of one data set from another. And so again, you see the gold line here. It's the difference of means in the example data set that I showed in the beginning. And the overall thing is following the Gaussian twin. You can also see that this sample mean is centered around 0.1, and it is kind of far away from 0, so it tells us that the dices are different in their means. On the other hand, on the right side, we see that when you compare A and C dices this way, you don't see that much difference. That's because they are more or less centered at the same mean, but they have different variances. So using this, once we have this, we need to ask what we want to test. And this question means that you need to define your null hypothesis. Null hypothesis is a hypothesis that, in our case, says that the dice are the same. And we are going to check it based on the mean. If they have the same mean, then the null hypothesis should hold. If they have different means, then they are different dices, and the null hypothesis is rejected. And here you see it's like a transition from this lower thing to this. The null hypothesis bell looks like this. And you see that the example mean is falling here, and the overall sample mean distribution is shifted relative to the null distribution, at least for A and B. For A and C, we see that the null distribution and the real sample distribution is more or less the same. So it means that then we can normalize this stuff to get away from the real value means and variances to the normal Gaussian 0-1 distributions. And once we do that, we can estimate we can use this Gaussian to estimate the probability. Gaussian bell describes probability, and if you set some kind of point on it and see the value of the Gaussian, you can interpret it as the probability of your sample getting into this region.
Maybe I missed it, but for the benefit of the group, did you talk about what a null hypothesis is and what the null distribution means in that context? Or
No, I don't think so. What hypothesis?
null hypothesis, right?
Oh yeah, well, I talked
You-
about it here.
You're going to get to it?
I talked about
Oh,
it
you did
here,
talk about
yeah.
it. Just
So your null hypothesis is something that you want to test. You need to think about what your null hypothesis is in each case. In this case, our null hypothesis is the dice are the same, and
Well, the null hypothesis will always be the same. It will be that there's no difference in
Yeah.
means.
Yeah.
Yeah.
This is what you're
What you're thinking of is H1. That's your alternative hypothesis will be different in each case. But the null will be the same in each case, which is that the difference in means is 0.
That's what you were saying. I think.
kinda, yeah, but I think we will get to it.
Yeah.
Eventually. When we will try to compare A, B, S, C. We will see that we're going to use a slightly different null hypothesis. We'll get that. So I hope this was clear so far. So what we found out that we have central limit theorem gives us a way to estimate the probability of our sample data set to be obeying some kind of hypothesis or not. To finish this test, we need to do permutation. So this can be a little confusing, but the jump from here, from the previous slide to this slide is something like this. Here I'm showing the distribution of sample means. I'm sampling my data set many times, and I'm showing you the distribution here. In real life, you probably have only one data set, and you want to figure out if there is something inside this data set. You don't want to get 1,000 more data sets to prove your theory. And so what you can do is you can do permutation. So you have this initial data set that had some kind of mean. And what you can do, you can reshuffle the labels inside those data sets and recompute the distribution of differences of sample means. And null hypothesis will tell you that those distributions should be the same and should be centered around 0 and obey the Gaussian law. But our real observed difference in samples for the left case ABSB shows that the observed difference is falling behind the 2 sigma. So if you define your confidence interval as 2 sigma, like if your result falls inside 2 sigma, then you assume that your null hypothesis survived and the dices are the same. If it went outside this confidence interval, then you say that null hypothesis is rejected. And yeah. So this way you found a way to quantify the confidence of one hypothesis or another. And that's, I guess, the cool thing about central limit theorem and the whole stuff of statistical inference. And again, for the case on the right, with dices that have the same mean but different variances, this test did not detect that they are different, although you saw that the distributions are slightly different. So yeah, to summarize, I hope it was somewhat clear, but I have just redeveloped the permutation test that tests if 2 data sets have the same mean. So using this test, we were able to distinguish these 2 dices, A and B. One is biased towards 3, another towards 4. But we couldn't tell apart these dices, despite you can see they're obviously different. But their mean is the same, but their variances are different. Is there any way we can distinguish A and C? Turns out we can make a test for that if instead of comparing sample means, we compare sample variances. You remember that I showed this picture before. It shows the distribution of sample means. And on these distributions, you can see that A and B are different and A and C are not. If you compare sample variances instead, you will see that dice A and B are kind of the same-ish, but A and C are clearly different. They are very far apart in their sample variances, and they do not really overlap. And so if you repeat this whole stuff again, you define D as a difference in sample variances instead of sample means. Then you can say that under null hypothesis that states that sample variances should be the same. You can see where this sample D is relative to the null hypothesis. This picture shows it. So, and A and C are clearly different. Null hypothesis is here, and the observed sample variance, difference in sample variances is here. But for A and B, it's kind of in the middle, so we can tell them apart this time. And so you can normalize it to follow the Gaussian with centering 0 on variance 1. And then you can do the permutation test again. And so you see that this time A and B are falling inside the null hypothesis confidence interval, and A and C is not. Also, p-values here is 0, and here it's 8.083. So what did it taught me? I guess many of my problems with statistical inference were coming from my lack of understanding what I wanted to test. And it turns out that to figure out what you want to test, you need to think about what your null hypothesis is. Depending on the null hypothesis, you want to either design different tests or apply different tests.
I understand what you were saying before now. Yeah, so thank you for clarifying. Yeah. You were talking about with respect to like different kinds of statistical tests is what it seems like. Yeah.
Yeah, I guess. Statistical inference can infer something, but you can infer all sorts of things, and you need to use different tests for that.
Yeah, I think you make a great point is that you need to think about what you're testing for, because like this kind of inference is not going to allow you to talk about meaningful differences, like for example, in magnitude between data sets, right? Like average expected magnitude of difference. But it might allow you to talk about, okay, well, and there have been, like you've adapted this into a permutation test, which I like because I love permutation testing, but there are other distribution tests that have also been established to determine whether or not the distribution of one data set is different from the distribution of another data set. And so this is kind of like a permutation test analog of that, which is cool. Yeah. But then I guess the question is, how do you interpret that? Because it tells you that the data points are distributed differently, right? But then you have to interpret what that means. So that's one of the challenges with distribution type tests versus like a difference in means.
You need to somehow bridge this distribution around which to the hypothesis test and that which.
Yeah. I think your example also gives a lot more of the intuition behind p-values, right? Confidence intervals. You've sort of had some graphics that alluded to it, right? But that, you know, when you're trying to ask whether you can reject your null hypothesis or not, the p-value is exactly defining that confidence interval, right, around that mean. Right, you're looking at the tails really of this distribution when you define that p-value. You're sort of setting where that tail is and where you're sort of willing to make, you know, mistakes about the you know, the difference actually, you know, not being observed. But yeah, I mean, this is, you know, the thing you always see is that when you look at your confidence interval, if the confidence interval crosses 0, then you can't reject your null hypothesis. And this is a great, I think, demonstration of that, right? So the white lines are the confidence interval here, right? The tails will be defined based on that p-value.
And as a matter of fact, a lot of these distribution tests are actually used to check the assumptions of parametric statistical tests. Because if the variances of the groups are different, then it biases the statistical result in a way that fundamentally undermines the assumptions of the test. And so, for example, for the t-test, you know, it's not robust to differences in variance between the groups. It gives false positives a lot of the time.
Yeah.
When you you have difference in variance.
Are we gonna cover homogeneity of variance in this?
Well, that's what we're talking about.
That's kind of what we're getting at, yeah.
Yeah, I was just curious if
Different
it's,
tools.
okay,
Yeah.
I was just curious if it's gonna come up.
Well,
So
and
how
if
does
these,
FDR correction come into play with this as well?
I don't
That's
think
post hoc under.
yeah, you haven't addressed that yet.
I'm not gonna talk about it, but
You're-
it's
okay.
something like this next, I think.
It just basically, I always thought about it as the opposite of Bonferroni. That's kind of how I always thought about it. It makes it harder to reject sure I'm saying this right, reject the null. Yes, so it makes it harder to reject the null. That's.
I mean, Bonferroni does the same thing. Bonferroni is stricter,
Right.
but they're essentially, they're computed different ways. Bonferroni is just division by the number of tests. FDR estimates this parameter called lambda, which is then corrects, is used to correct your P values into Q values. But that estimation typically doesn't work unless you have a large number of P values, like a decent sample size of P values. So that's why like Bonferroni is still like really useful for like if you're doing like 4 tests, that you can just divide the P values by, or the threshold by 4, right? Because you won't be able to estimate that.
Yeah.
Like lambda, right?
But to get back to the
Sorry.
assumptions of these tests as well, you know, one thing that is very, very often missed is that the assumption of the Gaussianity of these differences is huge for these tests to even work, right? Because if you have this, if this distribution looks, you know, skewed or different, like you can't make any assumption about rejecting the null hypothesis based on this kind of testing, right? You often need non-parametric tests, and there are other things that we do, but and Spencer alluded to that. But
Yeah, but I think the great thing about a permutation test is that it is not non-parametric.
yeah, permutations are not parametric. Yeah.
Yeah, but there are other ways to look at the differences in distributions besides permutation tests.
Yes.
Like there's like
Rank sums.
Kolmogorov-Smirnov distribution test is quite often used to check for homogeneity of variance before you do a t-test.
There's a whole
Very
new-
important because like hardly anybody does it. Like,
Yeah.
But
it could really bias your result.
With the sampling still right. That's the thing. When you end up with a small sample.
Well, if you don't have a large enough sample, you shouldn't be conducting a test in the first place.
That's fair. But yeah.
You know?
The one last slide before I go to the paper is like an overview of other tests that are not based on permutation necessarily, or don't use the same assumptions. And so maybe you can help me with reviewing them or adding information. So basically, there are different categories of statistical tests. One of those category of ectomy difference is 1-2 tail tests. So one tail tests are useful when you know about the direction of effect you want to test. For example, maybe you have 2 groups of people, one of them are controls, another is patients. And patients are getting some kind of medicine that maybe lowers blood pressure. So you want to test if your medicine is actually lowering blood pressure, not that it is just different in the patient's group. So in this case, you need to use one test.
So some kind of a sign.
Yeah.
Okay.
On the other hand, if you just want to find out if your medicine is doing any effect, then you can use 2-tail test. Yeah, that's not very important. Another thing is paired and paired. That's basically there about if you can somehow match the samples from one data set to another, then you want to use paired test. If you cannot, if you have just bags of data and you want to compare them, then you need to use some paired test. An example for that is, imagine that you're making a study with patients, you are measuring their blood pressure before they take a medicine and after. So for each person, you have 2 like paired things, before and after. If you have this information, you can use paired test. But if somehow you messed up your data set and you cannot any longer match the before and after for each person, then you can just bag them into different bags, use non-paired test. And another thing is rank test. Maybe you can help me explain it, but it's basically about how you, what you compare about
What,
In
I'm
data
sorry,
sets.
what did you say?
rank test.
Oh, rank
Like
test, yeah.
median test.
Yeah,
It's a brand of non-parametric testing.
Mhm. Yeah,
I like it because it isn't skewed by outliers. Sorry, this is my bias. I like rank tests more because there's always gonna be an outlier.
Doesn't assume symmetric distribution. Yeah.
Yeah. Yeah, exactly.
Yeah.
I think rank test is what I was using so far, but not very like mindfully. I think Wilcoxon or
Yeah,
rank
Wilcoxon
pair
works.
test is something I was using for comparing the periodic models
Mm.
in CV validation.
Yeah, but in rank test, you have to have the paired variables, right? And so if you sort by one, so you have a pair of variables and you have n of them. If you sort the first element of that tuple, but according to first one, it just checks if the second one is also sorted accordingly. Or if you test the first one, the other one is not, or like it's just random uniform. There is no order there. So that's basically what it's looking at. My again primitive understanding.
Mhm. Yeah, I think I had an idea like you, and I didn't look at it very closely, but I think it can also work with non-paired things.
Yeah,
And the way you can make it is, imagine you have two data sets, you basically mix them up in the same bag, then you sort them, and then you see like the mean of the sorting indices for one data set and another. It's like, no, it's gonna be too much time. Let's keep.
You could say bootstrapping, right? That would
Not sure, maybe it is.
bootstrapping is permutation.
Okay.
No, there's a Mann-Whitney U test you can use for rank testing between independent groups.
Is it paired or not?
Not paired, yeah.
Well, okay, and now the paper. So I think this paper was in one of the Vin's newsletter. He sent it to everyone, and then I saw it. It's talking about how the pitfalls of using statistical tests for comparing machine learning models' performance, especially in cross-validation setup. So what it is about? Many tests assume that your samples are independent from each other. They are not correlated in any way. And when you're using cross-validation, it's many folds. You train one model on like folds 1, 4, then you train another model on folds 2, 5, and so on. And you get the scores from them on the test folds. But since the training data between the cross-validated models is kind of overlapping a little bit, at least by some number of folds, they are not, the results are not really independent. They can be correlated. And when the results are correlated, it means that the effective variance of results is greater than the variance that the central limit theorem based tests can tell you. And if this variance is bigger in reality, but you assume that it is lower incorrectly, then you can get a false positive result. Like your observed result fell beyond the Bell range that you find acceptable, but since the Bell is actually wider, it fall into the false positive range.
Was it like a do we need to do some kind of like multiple comparison correction or something? Is that what you're saying? Something else?
I think the problem is more fundamental than that.
Kind of, yeah.
If
So
they're suggesting that even post hoc, like if you corrected for multiple comparisons, I think there's still room for error there.
it's like if you look at this equation, so you assume that variance is something, and then you see how your thing is approaching the mean. If you see that it is approaching the mean but not very well, and it falls somewhere outside the bell, then you make a false positive prediction. can see it, then imagine that this is the variance you assume, and this is the true variance. It is wider because the samples are kind of correlated. You don't know that, you don't assume that. And if your result is falling here, and you assume that this is the variance, and you get a false positive, your null hypothesis is rejected. But in fact, it was within the variance. So that's a good point.
Those online, he just drew two distributions, demonstrating the alpha and beta.
So again,
Sorry, I'm just narrating for the people online.
So there's an interesting analog of this in neuroscientific research, where a lot of the time results are based on neurons collected from the same animal, right? And so they use those results to sometimes generalize conclusions to the population level. But really what that's telling you is about the neurons in that animal, right? It's not telling you about the neurons across, for example, all mice or all monkeys, right? And so it's a similar problem because the variance could be smaller, right, for that group of neurons because they're particular to that animal. Whereas if you looked at the population, the variance in the values you're looking at could be more spread out, right? Because all the neurons are coming from, maybe a handful of animals. So, I mean, it's a well-known problem. Like most neuroscientists are like well aware that that is like a limitation, but it's just an interesting analog. I think it's picking up on the same kind of
So what doesn't
dependence.
quite fit for me? Like, I agree with the idea, the issue of not capturing all of the variability, but what doesn't match for me is the idea that because they're correlated, the variance is bigger. I would think it's the other way around.
No, he's saying it's
Exactly.
smaller.
It would be smaller, right?
Right, so you're underestimating the variance. Yeah. And so because the variance is the denominator, that's gonna inflate your statistic.
But isn't that just the definition of a sample versus population? Like we know the sample mean might not be the same as the population.
Right, but then that changes your conclusion, right? Because then your conclusions are only generalizable to that animal, not to the population of animals.
So you have to use what, the central limit theorem to prove that that's applicable? So this.
No, ideally you would want to sample distributions that are not dependent across folds, for example,
I see, yeah.
or neurons from different animals, right? I mean, we don't have an infinite amount of money to do this stuff, which is why this is like an acknowledged limitation. But it is a similar like acknowledged problem, like in a lot of like wet lab research.
I see.
Like the neurons are dependent because they're coming from the same animal, right?
Yeah, there is something going on in the chat. I think it makes sense. So to finish it off, I guess, the thing that the paper is proposing to address this problem of correlated results is kind of modification to cross-validation, some performed many times on the half of the data sets. So if you have a data set, you can split it in half, and you can do cross-validation on each half, as many folds. And this way you get, if you use 5-fold cross-validation, you get 5 results for each half. You average them, and then you get one sample for computing statistics. You get something like average score for A and average score for B. After that, you can split your data set in half another way and do the same and get another sample of TA and TB. And if you do it enough times, then you get enough statistics on this.
I think we solved it with Alex. Well, Alex solved it. So can you, Pavel, explain what do they mean by correlated? Why are they correlated? What is correlated? How is correlated in any sense?
If you're using simple CV, then the results from one test fold and another test fold are a little bit correlated because the training data is overlapping between these test results.
I don't think so. I don't think that's a problem. I don't think what they mean by correlated. I think, and correct me if you have a better definition, correlation is the following. We have n folds, and we have sample I, whatever, image I, brain I, and if that image is in fold k, it will not be in any other fold. That's correlation. An image can only be in one of the folds. It's not randomly sampled, it belongs to only one of the folds, and so that is how correlation is introduced. I don't see another way, but maybe there is another way.
Yeah, I'm not sure.
Those the training folds don't matter. Only the testing folds matter for this test, for the statistical test.
But the result of the test fold is the test data plus the trained model.
No, no. Trained model, nobody cares. It doesn't matter here. Trained model just gives us a number.
Yeah, but this number is affected by the data it was trained on.
It doesn't matter. The test
Well,
fold.
I mean, I guess you can ignore it, but then it
No, I'm not. It's not that I can ignore it. It doesn't matter for the statement. It doesn't matter for statistical tests. All that matters for statistical tests is what you are testing it on, the numbers on the folds. Not what you trained it on, but how you like the sample that you produced.
Yeah, so he's saying that like if you do k-fold cross-validation, you're only reporting the validation score usually, right? And then if you do your statistical testing just on that validation score, I don't know if I agree with the idea that it's correlated.
Maybe it's not correlated, but not independently sampled sense.
It's not, yeah, not independently, randomly, uniformly sampled. That's
The,
for sure.
the folds are not independent because, as I said, a sample can be in one fold, but not in any other folds. That means not independent anymore. Okay, what Alex is saying, do not report or test on the folds. Keep a holdout data set and only sample the holdout data set number. So you will have your validation on holdout data set, right?
Yeah.
Say it again.
So you have k folds, but you also have a holdout data set. Train on k minus 1 fold and report a number on holdout data set, not on the kth fold. And that's what you're testing again. But then, Alex, this is the same data set that every model is applied to, right?
I mean, I think holdout data, I don't know.
So you have K models and they report their performance on the holdout data.
Right.
So
What I was going to maybe say is that my view of what counts as holdout data is even different from a training testing split, right? I think holdout data should be, yeah, it should be different from a fold, right? A fold is still not an independent sample.
Yeah, it doesn't. The holdout data is not part of any of the folds.
Yeah, it should be, in my mind, a separate data set. Even is usually should be used for testing.
No, but like you train K models because you're doing cross validation, K fold cross validation. So you can have K measurements, K predictions on the holdout set.
So there are two things, right? One thing is hyperparameter tuning, cross-validation used for that.
Yeah.
And the other thing is reporting error prediction. So prediction error. Prediction error you can hold out. That you don't train and you don't cross-validate on.
Yep. Yeah, if you do cross-validation, do your hyperparameter searching within that cross-validation set and report the same validation set that you did your hyperparameter searching on, that's very problematic.
Yeah,
a lot of papers do that.
And for cross-validation, the model that is being trained on the K-1 folds is conditioned on those K-1 folds.
Mhm.
So it does depend on that data set, on those K-1 folds.
Mhm. Yeah, that sounds like.
So the predictions on the left, on the kth fold for cross-validation will be dependent on the predictions of the other folds pointing to the other training, the other cross validation folds. Does it make sense? Because part of the training data will be the same. The models will be dependent on the same data, training data. The parameters of the model are conditioned on the data. So there is dependence between the model across different folds.
Yeah, I think that's what the paper is trying to say. And if it happens, then you need to be careful about what kind of test you're using, or you can get a false positive.
I guess what I don't understand is what is the test? Because you're reporting predictions. What is the test you do on the predictions after that?
Well, if you have predictions for 5 folds, then you can try to compare them to see if they are significantly different or not using some kind of test. It's like
So it's a bad use of crossover. Because they're supposed to be reporting on holdouts.
you can still use cross-validation, but if you use that, you need to take into account that the results are not independently sampled, and so it leads to a greater variance and more false positives when you're trying to do hypothesis testing.
But testing of what? I'm still not.
Testing something like, is this model performing better or not? Like, imagine that 2 models give you
So you're comparing
functions.
different, say, I don't know, autoencoder and I don't know, LSTM, something like that.
Yeah, it's like you want to compare 2 models, you train them on the same folds, you get kind of paired results, and you can compare them as distributions.
Okay, so you can't do it on the holdout. You have to do it.
If you do it on holdout, you get away from this problem that your results are not independently sampled, but it also is limited. You can only have only 1 holdout, and you still need to train the model on some. And if you instead merge this holdout into your whole data set and do cross validation, you get more effective data for training, but you need to be careful about how you compare models.
Is that the message in the paper?
Sure. I didn't read into it in detail. I guess the main takeaway from this whole talk is about when you're doing some kind of statistical inference and you are trying to figure out what kind of test you want to use, you need to understand what's you're trying to prove, what's your hypothesis, and basically start from there, understand that, and then choose your test.
Thank you. It was really a good talk.
Yeah, thank you.
Thank you.
No, wait, but what shall we do?
Study statistics.
No, okay, I didn't get my recipe. What should I do? But I know there is another talk that you have to go. Thanks, everyone.